All right, good morning or good afternoon. Today we're going to do a little bit of notes on relationship between moles and volume, which your packet yesterday gave you a little bit of an insight on, but we haven't done any notes or problems on it yet. Okay, so remember Avogadro, our guy, his original hypothesis was that equal volumes of gases that are held at the same under the same conditions, so same pressure and same temperature, have the same number of particles. So particles of different gases aren't all the same size. Some are bigger, some are smaller. But because gases have so much empty space between particles, the size of those actual particles doesn't matter because they're still not in a liquid or solid phase. Okay, so the size of those particles doesn't define how many particles can be held in a space. So the identity doesn't matter, but the pressure and temperature will affect how many particles can be in a given volume. So in science, we have these conditions called standard temperature and pressure. That just makes things a little bit easier to compare different research and things. So standard temperature means 0 degrees Celsius. So that's the freezing point of water. And pressure would be 1 atmosphere, which is also 101.3 kilopascals, which is the second value here. But usually we talk in atmospheres. So at standard temperature and pressure, 1 mole of particles of any gas, doesn't matter what it is, occupies a volume of 22.4 liters. Okay, so this 22.4, that's what we call the molar volume of a gas. So we can use molar volume as another conversion factor. So if you are given a gas and you're given that gas's volume, you can determine how many moles of that gas are in that volume, assuming that that container is at standard temperature and pressure. Okay, so we have two conversion factors as always. We would have 1 mole over 22.4 liters or 22.4 liters over 1 mole. So if you were given liters and asked for moles, you would be using this conversion factor because again, your liters would be over here. You'd want to cancel out your liters to get moles. If you were given moles and want to know the volume, then you would use this conversion factor to cancel out moles to get liters. There's another idea we haven't really talked about too much here, but that's density, which is always the mass of something over its volume. So different substances do have different densities and usually report this in grams per liter. Although that density of water that I gave you for the little stations, I gave it in grams per milliliters. So density and molar volume together for a gas can be used to calculate the molar mass of that gas just by canceling units, okay? So I have an example to go along with that. If a gas has a density that should say 1.964 grams per liters, what is the molar mass of the compound? Okay, so this grams per liter is just like grams per mole. We can write like 1.964 grams over 1 liter. Okay, that just helps with our dimensional analysis. And we want to know the molar mass of the compound. What is the unit for molar mass? It's grams per mole. Okay, so this grams we want to keep as is, but we're going to want to cancel out this liters and somehow turn it into moles, which, given the molar volume, we can easily do. So to cancel this unit, we're going to want liters on top, moles on bottom. So we're going to end up using this conversion factor, 22.4 liters over 1 mole. Okay, so again, your liters are going to end up canceling, and then you're going to end up with grams per mole. So my calculator, I would take 1.964 grams divided by 1, multiply by 22.4 divided by 1, which gets me 44 grams per mole for this gas. Okay, so those are all the notes that I wanted to get through today. I'll get you some practice problems on these types of things. Have a wonderful day.